Your OAuth tokens are too valuable to leave unprotected in memory, especially when your application needs to survive restarts. You'll see how to securely persist encrypted OAuth credentials to disk using FastMCP's Fernet encryption wrapper, ensuring tokens stay safe between sessions while keeping the authentication flow seamless. The pattern combines disk storage with strong encryption, so your app picks up right where it left off, without exposing sensitive data.
From FastMCP import client. From FastMCP client auth import OAuth. From key value, AO stores, disk import disk store. From key value, AO, wrappers, encryption import Fernet encryption wrapper. From cryptography, Fernet import Fernet. Import OS. Hash create encrypted disk storage. Encrypted storage equals Fernet encryption wrapper. Key value equals disk store. Directory equals / FastMCP / OAuth tokens. Fernet equals Fernet. OS. Environ OAuth storage encryption key. OAuth equals OAuth. MCP URL equals https //FastMCP cloud /MCP. Token storage equals encrypted storage. Async with client. https //FastMCP cloud /MCP auth equals OAuth as client. Await client ping.
This demonstrates the secure credential storage pattern combined with OAuth 2.1 authorization code flow with PKCE. The code shows how to handle user authentication for API clients while securely persisting sensitive tokens across sessions. What makes this distinctive is the separation between the authentication protocol implementation and the storage mechanism, allowing flexible security configurations without changing core logic. The pattern works by abstracting the OAuth flow into a reusable component that manages the entire authentication lifecycle, from token acquisition to refresh. The storage layer is injected as a dependency, enabling encryption and persistence without modifying the authentication logic itself. This follows the dependency inversion principle, where high-level modules don't depend on low-level storage details, just the interface contract. This approach matters because it solves two critical problems: secure credential handling and seamless token management. In production systems, you need tokens to persist between restarts, but can't store them in plain text. The pattern also handles the complex OAuth flow automatically, including PKCE for security and token refreshes. It's ideal for CLI tools, daemons, or any long-running process that needs authenticated API access without exposing credentials in code. Let's break it down line by line.
From FastMCP import client.
Imports the client class from FastMCP, the primary interface for interacting with MCP servers. This handles connection management, request routing, and protocol compliance for all MCP operations.
From FastMCP client auth import OAuth.
This imports the OAuth authentication handler for FastMCP. It manages secure token storage and refresh cycles, eliminating manual credential handling in client operations.
From key value, AO stores, disk import disk store.
This imports disk store, a persistent key-value storage implementation that saves data to disk. It handles token persistence between sessions, preventing repeated OAuth flows.
From key value, AO, wrappers, encryption import Fernet encryption wrapper.
Imports Fernet encryption wrapper, a transparent encryption layer that automatically encrypts all data before writing to disk and decrypts when reading. This prevents sensitive OAuth tokens from being stored in plain text, while keeping the storage interface unchanged for the calling code.
From cryptography, Fernet import Fernet.
Imports Fernet from cryptography, a symmetric encryption implementation for secure token storage. This handles the actual encryption-decryption of OAuth tokens before they're written to disk, preventing exposure of sensitive credentials.
Import OAuth.
Imports Python's OAuth module to access environment variables. Required here to securely load the encryption key from OAuth storage encryption key, keeping sensitive values out of the codebase. This follows the 12-factor app pattern for configuration management.
Hash create encrypted disk storage. Encrypted storage equals Fernet encryption wrapper.
This instantiates an encryption wrapper using the Fernet symmetric encryption scheme. It ensures sensitive OAuth tokens are encrypted at rest on disk, preventing exposure if the storage directory is compromised. The pattern combines a key value store with transparent encryption-decryption.
Key value equals disk store. Directory equals // FastMCP/OAuth tokens.
This initializes persistent disk storage for OAuth tokens. The disk store writes encrypted credentials to FastMCP/OAuth tokens, ensuring tokens survive between sessions while remaining file system backed. This follows the storage wrapper pattern, where the underlying store handles persistence, while encryption layers provide security.
Fernet equals Fernet. OS. Environ OAuth storage encryption key.
This initializes a Fernet encryption instance using an environment variable as the key. Fernet provides symmetric encryption, ensuring OAuth tokens are securely stored at rest while remaining accessible to the application. The environment variable approach keeps the encryption key out of source control, following security best practices. Closing parenthesis terminates the OAuth initialization block. This finalizes the configuration with the encrypted storage and MCP URL, making the OAuth object ready for authentication. The pattern ensures all required dependencies are properly injected before use.
OAuth equals OAuth.
Instantiates the OAuth authenticator with encrypted token storage. This handles secure token persistence between sessions while protecting credentials at rest. The encrypted storage prevents exposure if the local file system is compromised.
MCP URL equals https://FastMCP cloud/MCP.
This specifies the MCP server endpoint URL, required for OAuth to authenticate against the correct FastMCP instance, ensuring token requests and API calls route to the intended service.
Token storage equals encrypted storage.
This assigns the encrypted storage to OAuth's token persistence layer. It ensures OAuth tokens are encrypted at rest on disk, preventing credential exposure if the file system is compromised. The pattern separates storage concerns from encryption logic, making both components independently testable. This closing parenthesis terminates the OAuth class instantiation, finalizing the configuration with the encrypted storage backend and MCP URL. It's the last step before passing the fully configured OAuth instance to the FastMCP client for authentication handling.
Async with client. https://FastMCP cloud/MCP auth equals OAuth as client.
Context Manager pattern with async support. The async with ensures the FastMCP client connection is properly initialized and cleaned up after use, preventing resource leaks. This is the standard way to handle async client lifecycles in FastMCP.
Await client ping.
This sends a lightweight ping to verify the FastMCP connection is alive and responsive. Critical first operation after establishing a client It confirms the server is reachable before making actual API calls. The async await pattern handles the network request without blocking the event loop. Secure OAuth token storage. The client-side pattern we just implemented mirrors the server's encrypted storage approach, creating end-to-end security for credentials across the entire FastMCP ecosystem. Plaintext tokens in disk storage become permanent vulnerabilities, even if your server uses perfect encryption. Always wrap your storage backend in Fernet encryption wrapper to maintain the chain of trust from server to client.
The token that never touches memory remains everywhere in the system.